When we say that reality exists independently of how we describe it, we are making a claim that sounds simple, but is deeply unsettling once you truly follow it to its end. It means that the universe does not care about our language, our symbols, our equations, or even our intuitions. Long before humans evolved brains capable of forming concepts, stars were already burning, particles were already interacting, and processes were already unfolding. The universe did not wait for us to name space, time, matter, or energy before behaving the way it does. Our descriptions came later, shaped by survival needs, cultural habits, and the limits of perception. Human beings are pattern-making creatures. We survive by building internal models of the world. These models do not need to be perfectly true, they only need to be useful. A hunter does not need to understand quantum field theory to throw a spear accurately. A farmer does not need to know general relativity to plant crops according to seasons. In the same way, our most basic ideas about space and time arose not because they are ultimate truths, but because they worked well enough for navigating a medium-sized world at low speeds. This is where the danger begins. When a model works extremely well for everyday life, the mind begins to mistake it for reality itself. Space feels real because we move through it. Time feels real because we remember the past and anticipate the future. But usefulness is not the same as fundamentality. History shows this again and again. The sun appears to move across the sky, so for thousands of years humans described a universe where the sun orbited the earth. That description worked well enough for calendars, agriculture, and navigation, yet it was still wrong at a deeper level. What physics keeps revealing is that our most trusted descriptions are provisional. They are lenses, not mirrors. When we say, "This is space," or "This is time," we are not pointing to substances that exist independently in the way rocks or atoms do. We are pointing to frameworks that help us organize observations. These frameworks can be replaced without reality itself changing. The universe does not break when our theories change. Only our understanding does. At the microscopic level, this becomes painfully clear. In quantum mechanics, the world refuses to behave like our classical descriptions demand. Particles do not follow neat paths through space. They do not possess well-defined positions and velocities simultaneously. They exist as possibilities, tendencies, probabilities. The mathematical formalism works extraordinarily well, but it does not require particles to be somewhere, in the classical sense before interaction. Our language struggles here, because language evolved to describe solid objects moving through space over time. Quantum reality simply does not care. This creates a profound mismatch. We keep asking reality questions in the wrong language, and then feel confused when the answers make no sense. Where is the electron when no one is looking? What path does it take? These questions assume that space and trajectory are fundamental. Quantum mechanics responds by saying, in effect, that the question itself is misplaced. Reality continues to function perfectly well even when our descriptions collapse. The same pattern appears in our understanding of time. We experience time as a flowing present, with a fixed past and an open future. Yet the fundamental equations of physics do not contain a preferred now. They do not care which direction time flows. From the perspective of the equations, yesterday and tomorrow are treated symmetrically. The flow of time, so vivid in human experience, does not appear as a basic feature of the universe's underlying laws. This does not mean experience is fake. It means experience is not the same thing as ontology. The universe contains processes, changes, and correlations. Our brains interpret these as a moving present because that interpretation is adaptive. It helps us act. But adaptation is not evidence of fundamentality. The danger of confusing description with reality becomes even clearer when we consider how many different descriptions can explain the same phenomena. In physics, it is common to find multiple mathematical formalisms that produce identical predictions. They look different, use different concepts, and tell different stories, yet they all work. If one description were reality itself, this would be impossible. The fact that multiple incompatible pictures can describe the same universe tells us that none of them are the universe. They are tools. This is especially important when discussing spacetime. Spacetime is an extraordinarily successful model. It allows us to calculate planetary orbits, GPS corrections, gravitational waves, and black hole mergers with stunning precision. But success does not guarantee fundamentality. Newtonian gravity was successful for centuries, yet it turned out to be an approximation. Euclidean space works perfectly for architects, yet fails at cosmic scales. Each time, reality stayed the same while the description changed. The universe does not consist of concepts. It consists of whatever it consists of, regardless of whether our minds can comfortably imagine it. One of the most revealing lessons from modern physics is that reality is under no obligation to be intuitive. Intuition is shaped by evolution, not by cosmic truth. Our ancestors needed to throw rocks, judge distances, and estimate durations. They did not need to understand non-local correlations or emergent geometry. As a result, our intuitions are deeply biased towards spatial and temporal thinking. When we encounter a level of reality where those concepts break down, we experience confusion, not because reality is broken, but because our cognitive tools are mismatched. This is why the first keynote matters so deeply. If we do not fully accept that reality exists independently of how we describe it, we will cling to familiar frameworks. Even when evidence demands we let them go. We will insist that space and time must be real because we cannot imagine anything else. But imagination is not a reliable guide to fundamentality. There is also a philosophical trap hidden here. Many people unconsciously assume that if something cannot be visualized, it cannot be real. But visualization is a human skill, not a cosmic requirement. You cannot visualize a four-dimensional vector space, yet it is mathematically precise and empirically useful. You cannot visualize a quantum wave function, yet it predicts experiments with astonishing accuracy. The inability to picture something is not an argument against its existence. Reality does not come with a guarantee of mental comfort. Another crucial point is that descriptions are shaped by the questions we ask. If we ask spatial questions, we get spatial answers. If we ask temporal questions, we get temporal narratives. But if space and time themselves are emergent, then our questions are already framed within the very concepts that need explaining. This creates a loop where we keep rediscovering spacetime because we never stop assuming it. Breaking out of this loop requires intellectual humility. It requires admitting that our deepest concepts might be approximations, not bedrock. That is not a weakness of science, it is its greatest strength. Science progresses not by defending its models, but by abandoning them when better ones appear. When physicists explore ideas where space-time is not fundamental, they are not denying reality. They are respecting it. They are following the evidence wherever it leads, even when it leads away from the comforting scaffolding of everyday intuition. In some approaches, reality is built from networks of relations. In others, from information processes or algebraic structures. These ideas may sound abstract, but abstraction is often closer to truth than familiarity. Think of money. A bank balance feels real. It affects behavior, decisions, and emotions. Yet money is not a physical substance flowing through the world. It is an abstract relational system agreed upon by humans. Its reality lies in its effects, not in its material form. In a similar way, space and time may be relational systems that emerge from deeper interactions, real in their effects, but not fundamental in their essence. Accepting that reality exists independently of description also protects us from mistaking language for substance. Words like field, particle, wave, and dimension carry intuitive baggage. We imagine them as things. But in physics, they are placeholders in equations, elements of a model. They point toward patterns, not objects. Confusing the map with the territory leads to endless conceptual knots. The universe is not written in human language. Mathematics itself is not reality. It is a translation, a very powerful translation, but still a translation. The fact that mathematics works so well is remarkable, but it does not mean the universe is mathematics in the same way a book is made of paper. It means mathematics captures structural relationships that exist regardless of how we express them. At the deepest level, reality simply does what it does. It interacts, evolves, and remains consistent with itself. Our descriptions are attempts to follow along. Sometimes they succeed brilliantly. Sometimes they fail quietly until anomalies pile up. When they fail, reality does not apologize. This is why letting go of spacetime as a fundamental entity is not an act of denial, but of maturity. It is recognizing that a model can be indispensable and still not be ultimate. Space and time may remain extraordinarily useful for describing large-scale phenomena, just as classical mechanics remains useful despite being incomplete. But usefulness does not grant ontological privilege. The universe existed before space was a concept. It will continue to exist if future theories describe it without space and time entirely. Reality does not depend on our explanations. Our explanations depend on reality, and that is the most important shift of all. Once you accept that reality exists independently of how we describe it, you become willing to revise even your most cherished ideas. You stop asking whether the universe fits your concepts and start asking whether your concepts fit the universe. That is the mindset required to understand a cosmos where the universe is real, but spacetime may only be a story we tell about it. If we continue following this idea honestly, another subtle implication emerges. The moment we mistake our descriptions for reality itself, we stop learning. Progress in understanding the universe has never come from defending familiar concepts, but from questioning them. Every major shift in science began when someone noticed that reality kept behaving correctly even when the prevailing description failed. That failure was not a flaw in nature, but a message from it. Consider how often humans have tried to freeze reality into fixed categories. We once believed matter was made of indivisible atoms, solid and eternal. Then atoms dissolved into electrons, protons, and neutrons. Then those dissolved into quarks, fields, and interactions. Each time, something we thought was fundamental turned out to be a useful approximation. Reality did not become less real as these layers peeled away. It became richer, stranger, and more subtle. This pattern should make us cautious about treating space and time differently from past concepts. They feel more basic only because they sit closer to human perception. But perception is not a measuring device for fundamentality. It is a biological compromise. One of the strongest reasons to believe reality exists independently of description is that different observers, using different frameworks, can still agree on outcomes even when they disagree on explanations. Two physicists may use entirely different mathematical languages to describe the same experiment and still predict the same result. If their descriptions were reality itself, this would be impossible. The agreement lies deeper than the description. This tells us something profound. Reality is invariant under changes of description. It does not collapse when we change coordinates, perspectives, or conceptual tools. Spacetime itself already reflects this lesson. In relativity, there is no single privileged way to slice the universe into space and time. Different observers divide spacetime differently, yet the physical content remains the same. This is already a hint that space and time are not absolute features, but flexible bookkeeping devices. Push this further, and the idea becomes unavoidable. If there is no single correct way to define space and time even within spacetime theory, then spacetime is already less fundamental than we once believed. It behaves like a language with many dialects, not like an objective substance. At extreme scales, this flexibility turns into breakdown. Near the Planck scale, the smooth fabric of spacetime that relativity relies on stops making sense. Distances and durations lose clear meaning. Fluctuations dominate. Geometry becomes unstable. The equations that assume a background of space and time no longer apply cleanly. This is not a technical inconvenience, it is a conceptual warning sign. Reality is telling us that we are pushing a description beyond its domain of validity. There is an important emotional reaction to this realization. Many people feel that removing space and time from fundamentality makes the universe cold, abstract, or inhuman. In fact, the opposite is true. It makes the universe more honest. It frees us from forcing reality into shapes that only make sense to creatures like us. When space and time stop being fundamental, what remains is not nothingness but structure, relationships, constraints, regularities. The universe becomes a network of influences rather than a stage with actors on it. Events do not happen somewhere in advance, they happen, and where emerges as a way of organizing their connections. This is difficult to express in everyday language because everyday language assumes space and time at every level. Grammar itself encodes sequence and location. We speak in sentences that unfold in time and describe objects situated in space. Trying to describe a non-spatiotemporal reality using such tools is like trying to explain color using only sound. The limitation is not in reality, but in expression. Yet physics has learned to work within this limitation. Equations do not need imagery. They only need consistency. When physicists follow the math wherever it leads, they repeatedly encounter formulations where spacetime plays a secondary role or disappears entirely. In these formulations, reality is defined by relations between measurable quantities, not by positions in an invisible grid. This reinforces the first keynote at a deeper level. Reality does not owe us a story that feels familiar. It owes us nothing at all. Our responsibility, if we want understanding, is to adapt our stories to reality, not the other way around. Another revealing angle comes from information theory. Information is not a thing that occupies space in the same way an object does. It is a measure of correlation, a pattern, something that can exist wherever relationships exist. Increasingly, physicists find that describing the universe in terms of information captures its behavior more naturally than describing it in terms of objects moving through space. If information is fundamental, then space may be a derived concept emerging from how information is organized and shared. Distance becomes a measure of how strongly systems influence one another, not a primitive separation. Time becomes a measure of how correlations change, not a flowing background. This perspective explains why reality can remain perfectly well defined even if spacetime is not. What truly matters are the rules governing change and interaction. Space and time are convenient ways to summarize those rules at large scales, just as temperature summarizes molecular motion without being a molecule itself. Accepting this also resolves a common confusion. People often worry that if spacetime is not fundamental, causality must disappear. But causality does not require time as a substance. It requires order. It requires that some changes depend on others. That dependency can exist without a universal clock ticking in the background. Order is more basic than time. Similarly, locality does not require space as a container. It requires limits on influence. Even in theories where spacetime is emergent, there can still be constraints on which systems affect which others and how strongly. These constraints give rise to the appearance of spatial separation without requiring space to be fundamental. The deeper message is that reality is internally consistent even when our familiar concepts dissolve. This consistency is what science ultimately seeks. Not comfort, not imagery, but coherence. There is also a human lesson hidden here. When we insist that reality must match our descriptions, we project certainty where there should be curiosity. We confuse understanding with familiarity. Letting go of spacetime as fundamental is not about rejecting meaning, it is about expanding it. The universe is under no obligation to be built out of the concepts we evolved to use. It only needs to be what it is. Our task is to listen. And listening, in science, means paying attention to where our descriptions stop working. When we finally accept that reality exists independently of how we describe it, we gain a new kind of freedom. We are no longer defending ideas for emotional reasons. We are no longer shocked when the universe refuses to fit inside mental boxes. We become explorers again. This mindset is essential for confronting the idea that the universe is real, but spacetime is not. Without the first keynote fully absorbed, the rest sounds like wordplay or denial. With it absorbed, the idea becomes natural, even inevitable. Reality does not vanish when concepts change. Only our illusions do. And what remains after those illusions fall away is not emptiness, but a deeper, more resilient truth: the universe is doing something real, structured, and lawful, regardless of how we choose to describe it. When we say that space and time are models, not substances, we are challenging one of the most deeply rooted assumptions in human thought. For most of history, space was imagined as a vast empty container, and time as an invisible river flowing uniformly for everything in existence. These ideas feel so natural that questioning them can seem almost nonsensical, yet physics has steadily revealed that treating space and time as things in themselves leads to confusion, paradox, and ultimately contradiction. A substance is something that exists independently, something that can, at least in principle, be isolated, measured, or affected. A model, by contrast, is a structured way of organizing information. It is a conceptual tool that helps us predict outcomes and relate observations. The mistake humanity has repeatedly made is to confuse extremely successful models with physical substances. Space and time are perhaps the most successful models ever created, which is precisely why the confusion has lasted so long. In everyday life, space feels like something real because we move through it. Time feels like something real because events happen in sequence and we remember earlier moments. But this feeling arises from how our nervous systems process change and motion. It does not arise from direct access to the universe's fundamental structure. Our brains evolved to track relative positions and changes because those abilities improved survival. They did not evolve to perceive reality as it truly is at its deepest level. When physics began formalizing these intuitions, it inherited their limitations. Classical physics assumed a fixed background of space and time against which motion occurred. Objects moved through space as time flowed uniformly for all observers. This framework worked astonishingly well for centuries, but its success hit a flaw: space and time were treated as absolute substances, even though nothing in experience required them to be. The cracks appeared when measurements became more precise. Experiments showed that time does not pass at the same rate for all observers. Clocks tick differently depending on speed and gravity. Lengths contract depending on motion. If space and time were substances, they would not behave this way. Substances do not change their properties based on how you observe them. Models do. Relativity did not destroy space and time, but it transformed them. Space and time stopped being independent absolutes and became intertwined aspects of a single mathematical structure. More importantly, their measurements became observer-dependent. This was a crucial clue. Something that depends on perspective is unlikely to be a fundamental substance. It is far more likely to be a framework for organizing observations. Even spacetime itself, as powerful as it is, behaves suspiciously like a model. It can be sliced in infinitely many ways into space and time, depending on the observer. No slicing is privileged. No universal present exists. What counts as now for one observer is partly past or future for another. If time were a substance flowing through the universe, this would be impossible. There would be a single objective flow. Instead, we find flexibility, relativity, and symmetry, all hallmarks of a descriptive structure rather than a physical medium. The idea that space is a substance also fails under scrutiny. Empty space is not empty in modern physics. It seethes with fluctuations, virtual processes, and fields. But these fields do not live in space the way objects live in a container. They are defined through relations and interactions. Remove the relations, and space loses meaning. This suggests that space is not the stage on which physics happens, but part of the script we use to describe interactions. A powerful way to see this is to imagine removing all matter and energy from the universe. If space were a substance, something would still remain. A pure emptiness with structure. But physics gives us no way to detect or define such a thing without reference to physical processes. Without rulers, clocks, particles, or fields, space and time cannot be operationally defined. They evaporate as concepts when stripped of the things they are meant to relate. This is a key sign of a model. Models require inputs. They organize data. They do not exist independently of what they describe. The language we use hides this fact. We speak of space expanding, time flowing, spacetime curving. These metaphors are incredibly useful, but they also reify abstractions. We begin to imagine space as something stretchy and time as something that moves. But in the equations, nothing actually flows. Nothing stretches like rubber. These are visual crutches layered onto mathematics that encodes relationships, not substances. At small scales, the substance view becomes even harder to maintain. Quantum mechanics does not assign definite positions to systems except in relation to interactions. A particle does not sit at a point in space like a grain of sand on a table. Its position is a relational property that only becomes meaningful when measured. If space were a substance, position would be an intrinsic property. It is not. Similarly, time in quantum theory does not behave like a flowing entity. In many formulations, time is not even treated as an observable in the same way other quantities are. It enters as a parameter, a bookkeeping device for change, not as something that can be measured directly like energy or momentum. This asymmetry hints that time is not on the same ontological footing as physical quantities. When physicists attempt to merge quantum mechanics with gravity, the substance picture of spacetime becomes a liability. The equations struggle because they assume a smooth background of space and time while simultaneously demanding that everything be quantized. If spacetime were truly fundamental, it should fit naturally into the quantum framework. The fact that it does not suggests that spacetime is an emergent description that breaks down when pushed too far. Emergence is not a denial of reality. It is a recognition of layered description. Traffic jams are real, but they are not fundamental objects. They emerge from interactions between cars. Temperature is real, but it is not a basic ingredient of nature. It emerges from molecular motion. In the same way, space and time can be real at our scale while not existing as substances at the deepest level. This idea explains why spacetime is so effective and yet so fragile. It works beautifully where large numbers of interactions average out into smooth patterns. It fails where discreteness, fluctuation, and relational structure dominate. That is exactly how emergent models behave. Another sign that space and time are models is that they can be replaced without changing physical predictions. In certain formulations of physics, one can describe the same system using different variables, some of which do not look spatial or temporal at all. The physics remains the same. Only the language changes. Reality does not notice. If space and time were substances, removing them from the description would remove the physics. The fact that it does not is telling. The insistence that space and time must be substances often comes from a psychological need for grounding. Humans want a background, a place where things happen. But nature does not owe us a background. It owes us consistency. And consistency can exist without containers. What replaces substances is structure, patterns of interaction, constraints on change. These can exist abstractly without being embedded in space or time as we imagine them. Space then becomes a way of summarizing which interactions are strong and which are weak. Time becomes a way of summarizing the order and rate of change. This shift is subtle but profound. It means that space and time are not ingredients of reality, but bookkeeping tools. Extremely refined tools, but tools nonetheless. Accepting this does not make the universe less real. It makes our understanding more precise. We stop asking where space comes from as if it were a material thing. We start asking how spatial relationships emerge from deeper dynamics. We stop asking where time flows from. We start asking how order and change arise. The universe is not built out of space and time. Space and time are built out of the universe's behavior. That is the core insight of the second keynote. And until we absorb it fully, we will keep mistaking our maps for the territory, our descriptions for substances, and our intuition for truth. If we push this idea further, we begin to notice how deeply the substance view of space and time shapes not only physics, but human identity itself. We locate ourselves somewhere. We measure our lives in years. We define existence by being present at a place in a moment. When space and time are treated as substances, they feel like the ultimate containers of meaning. But once they are recognized as models, meaning shifts from location to relation, from duration to change. This shift resolves many long-standing puzzles that arise only because we assume space and time must be there in advance. For example, asking what happened before the beginning of the universe presumes that time existed prior to the processes that define it. If time is a model that emerges from change, then asking what came before change is like asking what is north of the North Pole. The question dissolves not because it is forbidden, but because it is misframed. The same applies to the question of where the universe is located. We instinctively imagine it sitting somewhere, embedded in a larger space. But this again assumes space as a container substance. If space is a model internal to the universe, then the universe is not in space. Space is in the universe. Asking where the universe is located becomes meaningless in the same way asking where all numbers are located becomes meaningless. Numbers are not inside space. Space is one of the things numbers can describe. Once this is understood, many conceptual anxieties evaporate. We no longer need to imagine hidden dimensions as literal extra rooms somewhere else. We no longer need to picture space-time as a fabric floating in nothingness. These images are metaphors, not necessities. They help intuition, but they are not reality. Another powerful implication appears when we think about measurement. Measuring space and time always requires physical processes, clocks, rulers, oscillations, interactions. We never measure space or time directly. We measure correlations between physical systems. A clock does not measure time as a substance, it measures repetitive change. A ruler does not measure space as a thing, it compares one object to another using a standard. Without processes, space and time are undefined. This operational dependence is crucial. Fundamental substances should not depend on the very things they are supposed to contain. Yet space and time do. They are parasitic on physical behavior. Remove behavior, and they vanish. This alone strongly suggests that they are not ontological primitives. When we cling to the idea of space and time as substances, we create unnecessary mysteries. We wonder what space is made of. We ask whether time flows faster in some regions. We debate whether space-time can tear or ripple as if it were cloth. But these questions often arise from metaphor, not necessity. They treat models as materials. By contrast, when we accept space and time as models, the focus shifts to what truly needs explanation, why certain patterns of interaction exist, why changes occur in particular orders, and why the universe exhibits stable regularities. These are questions about structure, not containers. This perspective also aligns with how physics actually advances. New theories rarely add more substances, they reorganize relationships. Electricity and magnetism were unified not by discovering a new material, but by recognizing a deeper structure connecting them. Gravity in relativity is not a force substance, but a manifestation of relational geometry. Each step moves away from substance thinking and towards structural thinking. Even fields, which are sometimes imagined as physical stuff filling space, behave more like mathematical entities encoding relations. They do not need space as a container. Space is part of how we describe the field's behavior. In more abstract formulations, the field comes first and space emerges as a convenient parameterization. This inversion is psychologically difficult because it reverses the order we learn as children. We learn about places first, then about relations. But fundamentality often runs in the opposite direction. Relations come first, places are summaries. The same is true of time. We feel time because our memory is asymmetric. We remember some states and not others. We experience anticipation. But none of this requires time as a flowing substance. It requires entropy gradients, information storage, and irreversible processes. Time, as we experience it, emerges from these conditions. The model of time captures this emergence efficiently, but it is not the source of it. This explains why time behaves strangely in extreme conditions. Near black holes or at quantum scales, the assumptions behind the time model fail. The flow becomes ambiguous, stretched, or undefined, not because time is breaking, but because the model is being applied beyond its range. Accepting space and time as models also reframes debates about determinism and free will. If time is not a substance flowing from past to future, then the future is not a region waiting to be filled. It is a set of potential relations that become actual through interaction. This does not magically solve philosophical problems, but it removes false constraints imposed by picturing time as a rigid track. Similarly, the idea that the universe is a block where past, present, and future all exist equally is a statement about a particular spacetime model, not about ultimate reality. Models can be static while what they describe is dynamic. Confusing the two leads to existential discomfort that is unnecessary. At a deeper level, recognizing space and time as models makes science more flexible. It allows physicists to explore theories where geometry is emergent, where causality is fundamental but temporal order is derived, where proximity is defined by interaction strength rather than distance. These theories may sound strange, but strangeness is often a sign that we are finally leaving intuition behind. There is also a methodological lesson here. Whenever a concept becomes impossible to define without circular reference, it is a sign that it is not fundamental. Space is defined by distances between things. Time is defined by changes in things. Neither can stand alone. They are relational summaries, not independent entities. This does not make them illusions in a trivial sense. Illusions disappear when examined. Space and time do not disappear. They persist because they are extraordinarily effective approximations. They are stable patterns that emerge reliably from deeper dynamics. But stability is not the same as fundamentality. Clouds are stable patterns in the sky. They are real, but they are not substances separate from air and water vapor. In the same way, space-time may be a stable pattern in the universe's behavior, real at large scales, indispensable for prediction, but not a basic ingredient. Once this is understood, a subtle shift occurs in how we think about explanation itself. Instead of asking, "What is space made of?" we ask, "What gives rise to spatial relationships?" Instead of asking, "Why does time flow?" we ask, "Why does change have an order?" These questions are more precise and less burdened by metaphor. The second keynote, Fully Absorbed, teaches intellectual restraint. It reminds us not to inflate successful descriptions into ultimate realities. It asks us to hold our most familiar concepts lightly, ready to revise or replace them when evidence demands. The universe does not need space and time to exist as substances. It only needs rules, consistency, and interaction. Space and time are how those rules appear to beings like us. And that realization is not a loss of meaning, it is a refinement of it. When we claim that physics works without assuming space-time is fundamental, we are not making a speculative or philosophical statement detached from practice. We are describing something that is already happening quietly inside modern physics. Much of the most successful physics we use today does not actually require spacetime to be a basic ingredient. Instead, spacetime appears as a convenient stage we add later, after the real work has already been done. At its core, physics is about predicting relationships between observations. It does not begin with space or time, it begins with regularities. When certain conditions are met, certain outcomes follow. The mathematical machinery of physics is built to encode these regularities with precision. Spacetime enters as a coordinate system, a way of labeling events so we can keep track of them. But labeling is not the same as constituting. This distinction becomes obvious once you look closely at how physical theories are actually constructed. In many formulations of quantum mechanics, the central object is not a particle moving through space, but a mathematical entity that encodes probabilities of interaction. The equations tell us how these probabilities change relative to one another. Nowhere in this core formalism does spacetime need to exist as a physical thing. It is introduced later, when we want to connect calculations to laboratory measurements. This is not an accident, it is a clue. If spacetime were fundamental, it would be unavoidable. Every correct description would need to build it in from the start. But instead, we find that physics often works perfectly well without it, and sometimes works better when spacetime is temporarily ignored. A striking example comes from quantum field theory. Despite the name, much of its power does not come from fields as objects spread across space, but from abstract algebraic structures that govern interactions. In some formulations, what matters most are commutation relations, symmetries, and conservation laws. These are statements about structure, not about geometry. Spacetime is used to organize these structures, but it is not what makes them work. Even more revealing is the fact that the same physical theory can often be written in radically different ways. One formulation may look explicitly spacetime, based with fields defined at every point. Another formulation may eliminate spacetime entirely and replace it with purely relational variables. Both produce the same predictions. Reality clearly does not care which version we use. This freedom would not exist if spacetime were fundamental. Symmetry provides another powerful insight. Modern physics relies heavily on symmetry principles, and these principles do not require spacetime as a substance. They describe invariants as things that remain unchanged under certain transformations. Some of these transformations involve space and time, but the deeper idea is independence from description. When a law remains true regardless of how you label space or time, it suggests that the labels are secondary. In fact, some of the most important symmetries in physics operate in abstract spaces that are not spatial at all. Internal symmetries govern particle types, charges, and interactions. These symmetries have no location, no duration, no distance. Yet they are essential to how the universe behaves. If spacetime were the foundation of all physics, such non-spatial symmetries would be impossible to explain. Instead, they fit naturally once we accept that spacetime is just one layer of description among many. The same lesson appears in thermodynamics and statistical mechanics. These fields describe systems with enormous numbers of components. At this scale, detailed spacetime trajectories become irrelevant. What matters are averages, distributions, and constraints. Temperature, pressure, and entropy do not live in spacetime as objects. They summarize collective behavior. And yet these summaries are not optional. They are indispensable for understanding reality at large scales. Once again, physics succeeds by stepping away from spacetime detail, not by clinging to it. This becomes even clearer when we look at gravity. General relativity is often cited as the ultimate spacetime theory, but even here, spacetime behaves less like a substance and more like a bookkeeping device. The equations do not describe spacetime acting on matter in isolation. They describe a relationship matter and energy constrain the geometry, and the geometry constrains motion. There is no spacetime without matter, and no matter without spacetime in this description. Neither exists independently. That is not how substances behave. When physicists try to quantize gravity, the trouble arises precisely because spacetime is treated as fundamental. The quantum framework expects everything to fluctuate, superpose, and interact probabilistically. A fixed spacetime background resists this treatment. Attempts to force it to comply lead to infinities and contradictions. This is not a sign that quantum theory is wrong. It is a sign that spacetime may not belong at the foundational level. As a result, many approaches to quantum gravity begin by removing spacetime entirely. They work with networks, graphs, algebraic relations, or informational structures. Only after solving the theory do they attempt to recover spacetime as an emergent approximation. Remarkably, this often works. Spacetime reappears as a large-scale pattern, not as an input. This should be taken seriously. When a theory functions better without a concept than with it, that concept is probably not fundamental. One might object that spacetime is still needed to connect theory to experiment. That is true, but it proves too much. Language is also needed to connect theory to experiment, but language is not fundamental to reality. Measurement devices have spatial extent and temporal duration, but that does not mean space and time are basic ingredients of the universe. It means our interface with reality is spatial and temporal. Physics does not describe reality directly. It describes the interface between reality and observation. Spacetime belongs largely to that interface. Another revealing point is that many physical quantities we consider fundamental are defined without reference to spacetime. Charge, spin, and quantum numbers do not require distance or duration. They are intrinsic relational properties that manifest through interaction. Even mass, often thought of as deeply tied to spacetime, can be understood through symmetry, breaking mechanisms that do not depend on geometry in a primary way. If physics can define and predict these properties without spacetime, then spacetime cannot be the foundation on which everything else rests. The success of computational physics also illustrates this point. Simulations of physical systems often operate on abstract data structures. Space and time are discretized, approximated, or replaced by algorithmic steps. Yet the predictions match reality with extraordinary precision. This would be impossible if spacetime were a substance whose continuity and existence were essential to physical behavior. Instead, spacetime proves to be flexible, replaceable, and secondary. There is a deeper philosophical implication here. When we say physics works without spacetime as fundamental, we are saying that causation, correlation, and constraint do not require a background arena. They require only consistency. Events can influence one another without being embedded in a pre-existing grid. Order can exist without flow. Structure can exist without extension. This challenges not only intuition, but habit. We are used to asking where and when as primary questions. Physics increasingly suggests that how and in relation to what are more fundamental. Location and time are answers derived later, not starting points. Historically, this is not unprecedented. Forces were once thought to require direct contact. Action at a distance seemed absurd. Yet gravity worked without contact and electromagnetism followed. The problem was not reality, it was the assumptions we brought to it. Today, spacetime may be playing the same role that contact once did, an assumption that feels necessary until we learn otherwise. Another sign that spacetime is not fundamental is the way physics handles scale. At different scales, different descriptions dominate. At atomic scales, classical space and time fail. At cosmic scales, quantum detail washes out. If spacetime were fundamental, it should govern all scales equally. Instead, it behaves like an effective theory, powerful within a certain range, unreliable outside it. Effective theories are not mistakes. They are achievements. But they are not the final word. Accepting that physics works without assuming spacetime is fundamental does not diminish the achievements of spacetime-based theories. It contextualizes them. It places them where they belong, as extraordinarily successful approximations that capture large-scale patterns while hiding deeper structure. This perspective also encourages creativity. Once spacetime is no longer treated as sacred, physicists are free to explore radically different foundations. They can ask whether reality is fundamentally discrete or continuous, informational or algebraic, relational or process-based. These questions are impossible if spacetime is assumed from the outset. Most importantly, this keynote teaches discipline. It reminds us to judge concepts by necessity, not familiarity. If physics can function, predict, and explain without invoking spacetime as a primitive, then spacetime does not qualify as a primitive. It becomes a derived concept, powerful but contingent. Reality does not collapse when spacetime is removed from the foundation. Physics does not stop working. In many cases, it becomes clearer. And that is the most compelling evidence of all. When this insight is carried to its logical conclusion, it reshapes how we think about explanation itself. If physics works without assuming spacetime is fundamental, then spacetime cannot be the ultimate answer to why questions. It becomes something to be explained, not something that explains everything else. This reversal is subtle but transformative. Traditionally, space and time have been treated as the final background. Events happen, because they occur at certain places and times. But once spacetime is no longer fundamental, this logic inverts. Events do not happen because of where and when they occur, where and when emerge because of how events relate. The order of explanation flips. This helps clarify why so many deep problems in physics seem intractable when approached through spacetime first thinking. Questions like why the constants of nature have the values they do, or why the universe exhibits the dimensionality it does, become mysterious only if spacetime is assumed at the start. If spacetime is emergent, then these features are consequences of deeper rules, not arbitrary givens. One of the strongest confirmations of this approach is the way modern physics increasingly emphasizes processes over positions. Scattering experiments, for example, do not fundamentally care about where particles in space at all times. They care about inputs and outputs, probabilities of transitions, and conserved quantities. The calculations can often be performed without ever visualizing a trajectory. Spacetime diagrams are added later as interpretive aids. This is not a limitation of current understanding. It is a strength. It means that physics has learned to detach itself from imagery and rely on structure. Imagery is helpful, but it is optional. Structure is not. Another powerful confirmation comes from the role of computation and algorithms in theoretical physics. When physicists model complex systems, they often work in abstract state spaces that have nothing to do with physical space. Time becomes a sequence of computational steps, not a flowing dimension. Yet the results accurately describe real-world phenomena. If spacetime were fundamental, this substitution would destroy predictive power. It does not. In fact, this substitution often clarifies behavior that is opaque in spacetime terms. Chaotic systems, phase transitions, and emergent order are frequently easier to understand when spacetime detail is suppressed. This suggests that spacetime can obscure as much as it reveals. There is also a consistency argument. Fundamental entities should not depend on the very theories they are supposed to ground. Yet spacetime appears differently in different theories. Newtonian time is absolute. Relativistic time is observer-dependent. Quantum theory treats time asymmetrically or externally. If time were fundamental, it should appear consistently across frameworks. Instead, it shifts form depending on context. That is the behavior of a model, not a substance. The same applies to space. Classical space is Euclidean. Relativistic space is curved. Quantum approaches suggest discreteness or non-locality. The shape of space depends on the theory, which means space is not the bedrock. Bedrock does not change shape when theories change. This variability would be impossible if spacetime were ontologically basic. Once we accept this, many conceptual tensions relax. We stop worrying about how spacetime can emerge from nothing. It does not emerge from nothing. It emerges from something deeper that never needed to be spatial or temporal in the first place. The emergence is not magical. It is structural. This also reframes the search for a theory of everything. Such a theory is unlikely to be a spacetime theory. It will likely describe rules for how information, relations, or processes combine. Spacetime will appear as one of the large-scale solutions to those rules, not as the arena in which the rules operate. This explains why attempts to unify physics by quantizing spacetime directly often run into conceptual dead ends. They try to treat a derived concept as fundamental. It is like trying to explain fluid dynamics by quantizing waves instead of molecules. You can do it approximately, but the deeper explanation lies elsewhere. There is a lesson here about intellectual patience. Physics often advances by removing assumptions, not adding complexity. The removal of absolute space and absolute time was one such advance. The removal of spacetime itself as fundamental may be the next. Importantly, this does not mean spacetime is not real in any naive sense. It is real in the way weather patterns are real. They exist, they matter, and they can be studied scientifically. But they are not the deepest layer of explanation. Treating them as such leads to confusion. This layered view of reality aligns with how knowledge works in every other domain. Biology does not reduce to chemistry in any simple way. even though it depends on it. Psychology does not reduce cleanly to biology. Each level has its own effective descriptions. Spacetime is one such level. The mistake is to assume that because spacetime is universal in experience, it must be universal in ontology. Experience is not a reliable guide to fundamentality. Once spacetime is seen as emergent, the idea that the universe is real, but spacetime is not, becomes less shocking. The universe is the totality of whatever exists and interacts. Spacetime is one way that interaction organizes itself at a certain scale. The reality lies in the interaction, not in the grid we draw around it. This perspective also restores a sense of openness. It reminds us that our current theories, however successful, are not the final word. If spacetime itself can be revised, nothing is immune to questioning. That is not a threat to science. It is its essence. Physics does not succeed because it finds unchangeable foundations. It succeeds because it finds better approximations. And in this case, the approximation called spacetime may be one of the greatest ever invented, but not the deepest. When we say that events matter more than locations, we are shifting attention away from where something happens and toward what actually happens. This may sound like a small change in emphasis, but it carries profound consequences for how reality is understood. Human intuition is trained to think in terms of places. We ask where an object is, where an event occurred, where something will happen next. Location feels like the anchor of existence. Yet modern physics increasingly suggests that anchoring reality to location is a convenience, not a necessity. An event is an interaction, a change, a correlation between systems. It is something that happens regardless of how we label it spatially. A location, by contrast, is a coordinate assigned within a chosen framework. Coordinates can change without altering the event itself. Two observers can disagree about the spatial position of an event and still agree completely about its physical consequences. This alone tells us that location is not the essence. In relativity, this lesson is unavoidable. Different observers slice spacetime differently, assigning different spatial coordinates and different times to the same event. Yet the event remains the same physical occurrence. A particle decays. A detector clicks. A signal is received. The physics does not depend on where an observer chooses to place the axis. What matters is the network of causal relationships connecting events, not their embedding in a particular coordinate grid. This becomes even clearer in quantum mechanics. Many quantum processes cannot be cleanly localized in space. An interaction may involve correlations that span large distances, or states that do not correspond to definite positions at all. Attempting to force such processes into precise locations often creates paradoxes that dissolve once we stop insisting on spatial primacy. The event is the interaction itself, not the place we try to assign to it. Thinking in terms of events also clarifies the nature of causality. Causes and effects are relations between events, not between points in space. What matters is which events can influence which others and under what conditions. Space enters only as a way of summarizing limits on influence at large scales. At a deeper level, influence is constrained by rules, not by distance as a primitive. This perspective also aligns with how experiments are actually described. Experimental reports do not fundamentally care about absolute locations. They care about what was prepared, what was measured, and what outcome occurred. The spatial arrangement of equipment matters only insofar as it affects interactions. If the same pattern of interactions can be achieved in a different spatial configuration, the physics remains unchanged. Once events take priority, many conceptual confusions fade. Questions like, where exactly was the particle before measurement, lose their urgency. The meaningful question becomes, what interactions were possible and which one occurred? Location becomes a derived narrative, not a fundamental property. Even at cosmological scales, this shift is powerful. The universe is often pictured as a vast space containing objects, but it can just as well be understood as a vast history of events: nucleosynthesis, star formation, galaxy mergers, and so on. These events define the universe's structure. Space is the bookkeeping system we use to organize them. Recognizing that events matter more than locations does not deny space its usefulness. It puts it in its proper place. Space is a way of summarizing how events are related, not the reason those events exist. The universe is not a collection of things sitting somewhere. It is a web of happenings, and location is only one way, often a convenient one, of keeping track of that web. This shift is essential for understanding a reality where space-time is not fundamental. If space were primary, removing it would remove meaning. But if events are primary, meaning survives perfectly well without fixed locations. The universe continues to happen, regardless of how we choose to map it. When we say that quantum mechanics challenges geometric intuition, we are acknowledging a deep conflict between how the human mind expects reality to behave and how reality actually behaves at its most fundamental level. Geometry is one of the oldest intellectual tools humans possess. We instinctively believe that objects have shapes, positions, paths, and boundaries. These ideas are so deeply ingrained that we rarely notice them, yet quantum mechanics repeatedly shows that these geometric expectations are not built into reality itself. They are habits of thought. In the everyday world, geometry works because large numbers of microscopic interactions average out into stable patterns. A table has a shape, a ball follows a path, a room has a size. At this scale, space appears smooth, continuous, and reliable. Our brains evolved to operate at this level, so geometric thinking feels like common sense. But quantum mechanics operates in a regime where this averaging no longer applies, and the results are profoundly counterintuitive. At the quantum level, particles do not behave like tiny objects moving through space along definite trajectories. They are not little balls with well-defined positions. Instead, they are described by mathematical structures that encode probabilities of interaction. These structures do not live in ordinary three-dimensional space. They exist in abstract spaces that have no direct geometric interpretation. Geometry enters only when we force these abstract descriptions back into classical language. This is why quantum behavior seems strange. We try to visualize something that cannot be visualized. We ask for pictures when the theory offers relationships. The discomfort we feel is not a failure of the theory, it is a mismatch between expectation and reality. One of the clearest examples is the wave-particle duality. We try to imagine a particle sometimes behaving like a wave and sometimes like an object. But both images are wrong. The quantum entity is neither a wave in space nor a particle in space. It is something else entirely, something that only looks wave-like or particle-like under specific experimental conditions. Geometry is not the foundation here, interaction is. Entanglement pushes this challenge even further. Two quantum systems can become correlated in such a way that their properties are linked regardless of spatial separation. From a geometric perspective, this seems impossible or even mystical. How can something here be connected to something far away without anything traveling between them? The confusion arises because we assume spatial separation must limit connection. Quantum mechanics shows that this assumption is not fundamental. Correlation does not require proximity in space. This does not mean that space is irrelevant. It means that space is not the primary constraint we thought it was. The rules governing quantum systems are written in terms of correlations and probabilities, not distances and paths. Geometry becomes a secondary description that emerges when systems interact with their environment in classical ways. Another example is the uncertainty principle. We often interpret it geometrically, imagining a fuzzy particle smeared out in space. But the principle is not about measurement disturbance or spatial blurriness. It is about the mathematical structure of the theory. Certain quantities simply cannot be simultaneously well defined. This limitation exists regardless of any spatial picture we try to impose. Geometry fails because it is not the right language. Quantum tunneling offers yet another blow to geometric intuition. Classically, a particle must have enough energy to cross a barrier in space. Quantum mechanically, systems can exhibit effects on the other side of a barrier, without ever having a classical trajectory through it. The geometry of barriers and paths becomes a misleading metaphor. What matters are allowed transitions, not routes, through space. All of this points to the same conclusion: geometry is not the foundation of quantum reality. It is an emergent, approximate framework that works only when quantum effects are suppressed. When we insist on geometric explanations at the quantum level, we generate paradoxes that vanish once we let go of that insistence. This has deep implications for the idea that spacetime is not fundamental. If quantum mechanics, our most accurate theory of matter, does not rely on geometric intuition, then geometry cannot be the bedrock of reality. It must arise from something deeper, something non-geometric. The challenge is not that quantum mechanics is weird. The challenge is that our minds are used to geometry as a primary organizing principle. Quantum mechanics invites us to abandon that comfort and accept a reality structured by rules and relations rather than shapes and locations. Once this shift is made, the universe begins to look less like a machine built from parts arranged in space, and more like a network of potential interactions. Geometry becomes a useful map of that network at large scales, not the territory itself. Quantum mechanics does not destroy geometry. It puts it in its place. It shows us that geometric intuition is a tool, not a truth. And recognizing this is essential for understanding a universe that is real, even if spacetime is not fundamental. When we say that the universe is relational, not spatial, we are proposing a shift away from thinking of reality as a collection of things placed somewhere and toward thinking of it as a web of relationships that exist whether or not we describe them with space. This idea does not deny the usefulness of space. It questions its primacy. It suggests that what is most real is not where things are, but how they are connected. Human intuition begins with objects. We see a chair, a tree, a person. Then we notice where they are located. Spatial separation feels like the most basic fact about existence. But this is a cognitive shortcut. Our brains are optimized to track relative positions because doing so helps us survive. That does not mean relative position is the foundation of reality. It means it is the foundation of perception. A relational view starts from a different premise. It begins with interaction. Something affects something else. A change in one system correlates with a change in another. These correlations are primary. Only afterward do we summarize them using spatial language. Distance, direction, and location become ways of describing the strength, delay, or pattern of interaction, not independent facts. Physics increasingly supports this view. Many fundamental laws are written entirely in terms of relations. Conservation laws describe how quantities change relative to one another. Symmetries describe invariances under transformation. Quantum mechanics describes correlations between measurement outcomes. Nowhere in these foundational structures is there a requirement that space exist as a container. Even in classical mechanics, space quietly plays a secondary role. What truly matters is not absolute position, but relative position. Only differences in location have physical meaning. This alone hints that space is not a substance but a relational construct. Absolute space, once thought essential, turned out to be unnecessary. Relativity made this explicit. There is no preferred frame of reference, no universal grid. Every description of space depends on relations between observers and events. The universe does not come with built-in coordinates. Coordinates are chosen. Relations are discovered. Quantum theory pushes this further. Entangled systems behave as a single relational entity regardless of spatial separation. The strength of their connection is not diminished by distance in the way classical intuition demands. From a relational perspective, this is not mysterious. Distance is not fundamental, connection is. This does not mean everything is connected to everything else equally. It means that the structure of connections is what defines reality. Some relations are strong, others weak. Some are immediate, others delayed. Space is one way of organizing these patterns when the network becomes large and regular. A helpful analogy is language. Words are not meaningful because of where they are written on a page. They are meaningful because of how they relate to other words. Grammar is relational. Meaning arises from structure, not from position. In the same way, physical meaning arises from how systems relate, not from where they sit in an abstract space. This perspective also clarifies the nature of objects. An object is not a self-contained entity occupying a region of space. It is a relatively stable pattern of relations. An atom is defined by how its components interact. A molecule is defined by bonding relationships. A solid object is defined by vast networks of electromagnetic interactions. Remove the relations and the object disappears, even if you imagine the space remaining. From this view, space is a summary, not a foundation. It is a way of compressing information about relations into a form that is easy for human cognition to handle. Near things interact strongly and quickly. Far things interact weakly and slowly. We encode this pattern as distance. But distance is not the cause of interaction strength. It is the label we give to it. Time fits naturally into this relational picture as well. Temporal order is not a river flowing independently of events. It is a way of describing how changes depend on one another. One event enables another. One process constrains the next. Order arises from dependency, not from a universal clock. When the universe is understood relationally, many conceptual problems dissolve. The question of where spacetime comes from becomes the question of how stable patterns of relation arise. The question of why the universe has the geometry it does becomes the question of why interactions organize themselves the way they do. This also changes how we think about boundaries. In a spatial view, boundaries are physical edges. In a relational view, boundaries are defined by interaction strength. Systems are separate, not because there is empty space between them, but because their interactions are weak. Systems are together because their interactions are strong. Space encodes this distinction but does not create it. Importantly, a relational universe is not vague or mystical, it is precise. Relations can be quantified, constrained, and modeled mathematically. In many modern theories, networks, graphs, and algebraic structures replace geometric pictures. These tools describe how elements connect without presupposing space. Space emerges later as a convenient visualization. This is why the relational view fits naturally with the idea that spacetime is not fundamental. If relations are primary, then spacetime is one-way relations appear when averaged over many interactions. It is not the stage on which relations occur. It is the pattern relations take at large scales. Accepting this requires letting go of the comforting idea that reality must be built like a room full of furniture. Reality may be built more like a conversation, a computation, or a web. Meaning lies in connection, not in placement. The universe is not a collection of things sitting somewhere. It is a structured set of relationships continually updating themselves. Space is how that structure looks when translated into human intuition. And once this is understood, the idea that the universe is real while spacetime is not fundamental stops sounding radical. It sounds precise. When we say that understanding improves when we let go of familiar frameworks, we are pointing to a pattern that runs through the entire history of human knowledge. Progress has never come from protecting intuition, it has come from challenging it. Each time we loosen our grip on what feels obvious, reality becomes clearer, not more obscure. The idea that spacetime may not be fundamental is only the latest example of this long tradition. Familiar frameworks feel safe because they are deeply embedded in perception, language, and culture. Space and time, in particular, feel unavoidable because every human experience is filtered through them. We remember the past, anticipate the future, and move through environments. This makes it easy to assume that space and time must be the foundation of everything that exists. But familiarity is not evidence of truth. It is evidence of repetition. When science first suggested that Earth moves around the sun, the idea felt absurd. The ground beneath our feet feels still. The sky seems to revolve around us. Letting go of that framework required intellectual courage. But once it was abandoned, celestial mechanics became simpler, more unified, and more predictive. The universe did not become more confusing, it became more coherent. The same pattern appeared when absolute time was questioned. For centuries, time was assumed to tick uniformly for all observers. This assumption fit everyday experience, so it went unchallenged. But when evidence forced scientists to abandon it, the result was not chaos. It was relativity, a framework that explained phenomena previously considered paradoxical. Letting go of absolute time did not destroy physics. It completed it. These examples reveal an important lesson: the frameworks that feel most obvious are often the most limiting. They shape the questions we ask, the answers we accept, and the problems we think are possible. When a framework becomes invisible, it becomes dangerous. We stop noticing that it is a choice. Letting go does not mean discarding everything at once. It means holding concepts provisionally. It means being willing to treat even the most trusted ideas as tools rather than truths. This attitude is not skeptical in a destructive sense. It is disciplined. It respects evidence more than comfort. In the context of spacetime, this discipline is crucial. Many conceptual knots in modern physics arise because we try to force new phenomena into old frameworks. We insist on asking spatial questions about entities that do not behave spatially. We demand temporal narratives for processes that do not unfold in a simple time sequence. The resulting confusion is not a sign of mystery in nature. It is a sign of mismatch between framework and reality. When we loosen that grip, new forms of clarity appear. Problems that once seemed metaphysical dissolve into technical ones. Questions that sounded profound turn out to be artifacts of language. This is not a loss of depth. It is a gain in precision. There is also a psychological dimension to this process. Letting go of familiar frameworks can feel like losing meaning or certainty. Space and time give us orientation. They tell us where we are and when we are. Abandoning them as fundamental can feel destabilizing, but this discomfort is temporary. What replaces it is a deeper sense of coherence, grounded not in intuition, but in consistency. Understanding improves because we stop asking the universe to fit our expectations. We start adapting our expectations to the universe. This shift is subtle but profound. It transforms science from a search for confirmation into a dialogue with reality. Another benefit of letting go is creativity. New frameworks allow new questions. Once space and time are no longer assumed, physicists can explore ideas based on information, computation, or relation. These ideas might have seemed meaningless or unscientific under older assumptions. Now they become viable paths of inquiry. This openness does not mean anything goes. Constraints remain. Predictions must match observation. Consistency must be maintained. Letting go of familiar frameworks does not weaken standards, it sharpens them. When fewer assumptions are baked in, explanations must earn their place. There is also a humility built into this process. It reminds us that human cognition is not the measure of reality. Our brains evolved to survive, not to decode the universe at its deepest level. Expecting reality to align with intuition is a category error. Letting go is an act of respect for the complexity of the world. Importantly, letting go does not erase practical usefulness. Space and time will not disappear from daily life or engineering. Just as Newtonian mechanics remains indispensable despite being incomplete, spacetime will remain a powerful tool where it works. Understanding improves not by erasing tools, but by knowing their limits. This perspective also protects us from dogmatism. When frameworks are held lightly, disagreement becomes productive rather than threatening. Different models can coexist, each illuminating different aspects of reality. This flexibility is essential in a field where no single description is likely to be final. At a deeper level, letting go reveals a strange consistency in the universe. The less we insist on human-centered concepts, the more unified reality appears. Patterns repeat across scales. Relations matter more than containers. Change matters more than flow. Structure matters more than imagery. This is not a retreat into abstraction for its own sake. It is a refinement of understanding. Abstraction strips away what is not essential. What remains is often simpler, not more complex. The idea that the universe is real while spacetime is not fundamental can sound radical only if we cling to familiar frameworks as truths. Once we release that attachment, the idea becomes a natural extension of a long scientific tradition. Reality is under no obligation to make sense on our terms. Understanding improves when we accept that, not because we know less, but because we finally allow ourselves to know differently.